Welcome to Beyond BIM. In today's episode, I have the pleasure to discuss the future of computer vision in construction with Dr. Ioannis Brilakis. Dr. Ioannis is the Director of Construction Information Technology at the Department of Engineering at the University of Cambridge. Ioannis's research interests are predominantly in the field of construction engineering, but specifically focuses on the construction automation and information technologies. His research has included in generating and updating building and infrastructure digital twins, sensing and data collection for civil infrastructure development, infrastructure computer vision, and pattern recognition technologies used for construction site data analysis. Computer vision technologies are increasingly cropping up in the construction market, with new applications in health and safety monitoring particularly. In today's episode, Ioannis explains to us what lies underneath this technology and what the future may hold with reality capture and hybridized systems. And now, let's take a listen to what Ioannis has to say about the future of computer vision in construction and its role with digital twins. If you could just give us a brief introduction to yourself and what originally led you to conduct research into automation, computerization of the construction and the built environment in the first place.
Okay, sure. So my father was a general contractor in Greece, a small contractor with a few large pieces of construction equipment, doing a lot of road works, earthworks projects. And, as a kid, I went through this construction environment and all the struggles that they were going through. I always tended to be naturally more interested in computer science, but as happens quite often in those parts of the world, if your family is civil engineers, you might end up being a civil engineer because that's what the family trusts, and you kind of continue along that same route. That's a choice I have regretted, actually. I should never have become a civil engineer. I should have gone to computer science directly. But anyway, I made the choice when I was 18, went to civil engineering, studied in Greece. And then afterwards, I could quite well see that I wasn't suited for a contractor's career, certainly not in Greece. I wasn't particularly happy with the life that my father was going through and all the struggles he felt. So I decided to go another route. And at the time, went to the US, got a master's and PhD in Illinois, in the same field, in construction management, but with a focus in informatics. So finally, I got back into informatics a little bit. And ever since then, I never left. So I got my first sort of an academic post. I was effectively like a visitor at Carnegie Mellon for a year. But then I became an assistant professor in Michigan, 3.5 years. I then moved to Georgia Tech for another 3.5, until eventually I got the position in Cambridge and moved to Cambridge back in 2012. So it's been now 8 years. So anyway, been a long time since. In terms of the research and how it evolved, if I understood your question correctly, at the very beginning, I still remember my PhD supervisor saying, I work with text data, image data, and structured data databases. Choose one. And I said, okay, I like images. Can I do the images one? So that's how the whole thing started. I was his first student to go actually through a vision route. Initially back then we were still playing with, half transforms and very basic tools from the 90s and early 2000s. But the potential was there. There was a lot of potential. We could suddenly see that we could easily recognize materials in images, and then we could start recognizing some objects in images, and then we could start doing some tracking of mobile objects such as workers and equipment and other things. So clearly that was an area that was growing very fast in computer science, computer vision, and all of those advances had perhaps not direct, but nearly direct applicability within our sector in various problems. And so there was that potential, well, what can I do to take that method that perhaps doesn't work directly in our case, but what can I do to modify it and improve it and get it to a point where actually it solves our problems and our needs? So yeah, that's what got me into that direction.
And obviously with that research focus, you then went on to co-author a book with Carl Haas titled Infrastructure Computer Vision. So what was the original incentive for that book, and how has the research and maybe even some of the work in industry evolved since it was published?
Well, the research hopefully has evolved, but probably not too much because the book was only published 6 months ago. So it hasn't been long. But how we got to the book, I would say 2 events. One event was over time, you start building up a lot of material that students that you're bringing into your own group need to then go and synthesize themselves. And as time was progressing, I felt more and more a need to give them something that would really get them up and running much faster, rather than go and read papers and you synthesize everything yourself. So that was one motivator. The other motivator was I think it was the right time to start integrating all that knowledge together, given everything else that was happening in the industry at the time. It was the transition, moving gradually from BIM to digital twin, moving from the old school computer vision methods into the new machine learning based computer vision methods, moving from more simplistic problems such as detecting specific objects to start doing much more holistic scene understanding and exploiting the context in scenes a lot more. And there was already quite a lot of evidence to show that this was happening. This also came at the same time as I was going on a sabbatical, and my colleague Carl Haas was also on a sabbatical. And I was in Munich and he was in Switzerland, in Zurich, 3 hours from each other. So we said, great, perfect chance. We're on sabbatical. Now's the time to get a book out.
Let's say for the novice that isn't familiar with what you just discussed, computer vision, and you talk about the old school versus the new way of doing things, can you describe what is computer vision exactly?
Computer vision in general, in the scientific sense, or computer vision within our context?
Within our context of construction and built environment.
Perhaps to be a little bit more precise, I would take 2 areas. One, I would call it computer vision, which deals more with image data. And the other I would call computational geometry, which deals a bit more with 3D data, point clouds, and so on. Although these 2 are so close to each other that even on the science end, many colleagues would do one, would do the other, and alternate back and forth. So what do these 2 have in common? Well, both of them deal with what we call unstructured data. So to explain that better, the data in a database is very much structured data because they follow a very specific pattern and can be easily interrogated. The data in a text document is semi-structured because text does have some structure, and we can leverage that structure to exploit a lot of the information in it, particularly if it's HTML or web pages and so on. Images and point clouds, there's absolutely no structure. There is nothing you can hang on your hat to say, right, so I'm going to leverage this advantage to start understanding what's going on in the scene. And computer vision is the science of taking that data and getting something out of it. Now, that something is so diverse that it's difficult to explain, and it's different in different contexts. But I can give some examples in our space. We can use computer vision very effectively to monitor work on site. We can use it to detect changes, progress, and compare, for example, with a design model as part of doing that. We can use it to do even things like overheight detection. in the case of tall vehicles approaching a very low bridge. There's many examples of where this might be useful in infrastructure.
So in the space of construction tech, so we're seeing a lot more proliferation and discussion with the startups emerging within our sector that are trying to apply computer vision specifically. How do you see construction tech and businesses are going to have to change as a result of this technology entering the market?
There's, of course, a lot of applications, and perhaps I should focus on two which I see a very direct value from. One of it has to do with off-site manufacturing. The problem we have if we were to install cameras on-site is that the work on-site moves, but the building doesn't, right? Or the road and so on. So you have a fixed asset and then mobile crews that move around it to do work. And because it is the work we need to capture rather than the asset themselves in the case of tracking, we would have to move the cameras as well, and that's not practical. And so camera applications on site have very limited use cases. However, in the factory, it's the exact opposite. It is your components that move, and it's the factory that's static. So in those cases, you can really instrument your entire factory with lots of cameras and use those cameras to very accurately capture all the activity in there, as well as all the components being manufactured. So there is a fantastic use case there to help improve offsite manufacturing productivity by better monitoring the assets and helping with the whole logistics process. The other value is very much in the space of digital twins. Now, one of the key prerequisites for a data set to be able to be called a digital twin is that it has to replicate the physical twin. And that is not an easy thing to achieve, because that means you have to go from the physical back to the virtual. And we don't have easy methods of doing that. In the literature, it's very often reported across multiple publications that for example, 1 day of laser scanning an asset, you need to spend 10 days afterwards modeling it. And then we've seen examples like, for example, industrial facilities with data sets of the range of 30 to 40 billion points, data sets that we cannot open with a computer today. We have to open them piecewise and then stitch the results together. And it would take a crew of 6 people or 10 people 10 months to do the job. That's not practical. And that's why we talk about digital twins, but we don't have them. And we don't have them because the cost right now to produce them, let alone to keep them up to date, is massive. That's where computer vision comes in and can really make a huge impact, because we've seen with multiple examples over and over again how we can tackle this problem, for example, for bridges. We've already done that, bridges being the low-hanging fruit because everything's exposed. The number of object typologies is very small. We've seen that gradually for buildings, with more and more examples of how we can detect all the building components and make a model quickly. We are now publishing some first really good examples with deep learning for industrial facilities, and we will very soon be publishing examples for railways, roads, and other assets. So this is on its way. And like I said, it's very important because, for example, we can keep talking about machine learning on digital twins, but without a digital twin, you cannot do machine learning. You need the data first.
So there is a clear distinction that you make between the construction environment and also the type of infrastructure that you might be trying to capture. So in the case of computer vision, what we're most familiar with seeing is computer vision being trialed with autonomous vehicles. But how does that differ on a static road environment with a dynamic construction site?
Well, on a dynamic construction site, you still have two things that are of interest. One is the static asset, which is gradually being built. And the other is the dynamic resources that work around it to produce that gradually progressing asset. With regards to the static asset, the answer is that if you want to capture it over time during the construction process, well, that means you have to do a lot of, let's say, visits. And the visits could be with drones, could be with other kinds of devices. It could be with handheld devices inside and so on. With regards to resources, well, then it depends on the resource and the use case. And it goes back to the tracking problem. If I'm looking at, for example, tracking haulers, trucks, probably the best method is going to be with GPS, because haulers can go for kilometers. I cannot do that with a camera. But if I'm looking at a crew of 3 or 4 people, think of bricklayers putting down over a facade, it could also be captured with a camera. Again, it depends on the use case to decide what is the best technology to solve the problem.
You did already touch upon this in slight detail, but can you describe in a bit more about how we can utilize, as you discussed, computer vision, or in some instances photogrammetry, to help develop what is known as the Asbuilt BIM? You touched upon laser scanning, but maybe you can further elaborate on the difficulty with the Asbuilt BIM.
Well, first of all, we have to define the output. If I'm looking at a model in the end, to what level of detail do I want to capture it? Am I looking at capturing perhaps the model at a very low fidelity? Let's call it very low level of detail, where perhaps the entire asset is a box or just a few boxes. Or do I want to go all the way down to the reinforcement in the component, right? The reinforcement in the concrete. Right now, we're in a position where we can go somewhere in between. So in other words, everything that we can see. We are not yet in a position to go inside components and capture the things that are not immediately visible. And that's why we use laser scanners and cameras, because both of them capture only the visible world. And it is that visible world we're able to capture. We hope that in the future, using perhaps radar, sonar, and other technologies, we can also capture what's inside those components and go to even higher levels of detail. So I'll put that in a parenthesis and explain the sequence now. So for us to capture the visible model, as I would call it, the steps we usually follow is we start, first of all, with capturing raw data. Raw data in this context is simply pixels and points. Points from the scanners or from photogrammetry, videogrammetry, and pixels from the imagery. A second step from that is then to take that and somehow translate that into what we call higher level geometry. And that is something you can do in one or multiple steps. There are examples where people go from what I would call from points to lines to planes to objects to assemblies and up the hierarchy. There are, this is a bottom-up example. There are top-down examples where you have your entire asset as a single scan, basically multiple scans registered on each other. And then you start doing a hierarchical segmentation process. I have a building, let's cut out the floors. I have a floor, now let's segment the rooms. I have a room, now let's find all the walls around it, the ceiling, the floor, and so on. And of course, hybrid methods that exploit both a bottom-up approach as well as a top-down approach to address the problem. Once I've done that and I have a sense of reasonably good geometry with labels, in other words, these points, as we call it, a point cluster, belongs to object X, for example, a column, a beam, a wall, or something like that. The next step would be to fit within that space some sort of a representation. It could be that if I'm not interested in a lot of detail, I could just fit a cuboid or a cylinder or something, and then label that some sort of an IFC component. Or it could be that I can still keep it as an IFC component, but with the initial full geometry. For example, the mesh that is produced by wrapping a mesh around the cluster of points. What that gives us in the end, again, is just objects. The next thing we need after that is I want to capture relationships. That's very important because, as we said, perhaps not all the objects are visible, or not the entirety of an object is visible. And if I know these relationships, I can easily use that information to, let's say, shorten them or elongate them to make sure that they actually fit with each other. For example, we would expect walls to meet at the corner of a room. There wouldn't be a gap there. And I can use these kinds of assumptions to improve the fidelity of my outcome. Once I've detected both the objects and their relationships, and done, of course, any corresponding corrections, then I have what I would call a basic geometric model. And once I have that model, I can then easily do things like plaster the textures on top and detect things on those textures, or add structured data on top, text data, which could include anything from construction data, design data, operation data, and start gradually building that digital twin.
So it is quite an important prerequisite for the digital twin from what you're saying.
Yes, and I don't see how else can we do this. Like I said, a model is just a model, a BIM model, for example. For that model to be called a digital twin, I mean, it's a twin, right? It must twin a physical twin. And therefore, you need to make sure there is consistency between the two. And the only way to capture that consistency is using methods like that to capture the physical asset and digitize it, as we call it, or virtualize it.
When we look at some of the techniques of capturing what is actually built, you also discuss in your book about videogrammetry and photogrammetry. So is that technology reaching a stage where it's becoming accurate enough for us to use those techniques on site?
For a very long time, the answer has been yes and no. We're always in this intermediate state where we see some impressive examples, but actually they don't proliferate in practice because there's just another thing missing somewhere there that we need to address. For example, it's been a long time since devices like the Google Tango came along that allows you to pick up a device that looks like a tablet and walk around the building and get very, very high quality odometry, as we call it, that allows you to capture all the geometry internally of an asset. That has since been even more improved, but it still comes back to the same problem. This only works for short distances and in indoor environments. Once you go outside with the sunlight and you're looking at 20, 30, 100, 300 meters, you're no longer able to do that, and you get stuck with the old school laser scanners. That's why we're starting to do now more research into that direction. In other words, right, so we like the Tango, very good principle. How can I do that same thing outdoors? How can I increase my distances and improve performance? And I have a project running right now exactly in that space, funded by Topcon, Trimble, Langor, BP, and Geoslam, focusing exactly on that space with the use effectively of 3 high-quality sensors, a mini laser scanner, a computer vision camera, and a near-infrared camera put together in a single package, light enough, under 2 kilos, so that it can even be drone-mounted or handheld, and able to capture points, pixels, and near-infrareds all in the same raw data set registered to each other, and most importantly, real-time and progressively. That's important because you want to see the result as you go, so that if you don't like the result, you modify your scanning motion to fix what it is that you're not happy with. For example, you forgot to scan an area and you see an occlusion, you want to go there and capture that occlusion.
And I take it that this is what you call a hybrid method because you're combining the 3 different methods of capturing that data?
Yeah, the motivation behind this was that, the camera is great. We have massive resolution coming from the camera. The one we have is about 48 megapixels, 30 frames per second. So that's a massive amount of data coming in. So the density is there, but the accuracy is problematic. It has all the issues that traditional photogrammetry and videogrammetry has. On the other hand, the laser scanner, it's extremely accurate. We're looking at sub-centimeter accuracy at 100 meters, but it's extremely sparse. We get a very few points in the screen, given that it is a small sensor. Now, combining the two leverages the advantages of one and the advantages of the other to cancel out their common disadvantages. One gives you the accuracy, the other gives you the density. And that was the motivation from the beginning.
I take it it's not really a commercial product. Right now, you're trying to test it empirically to see whether or not this does improve the accuracy. So if somebody wanted to deploy this on site, would they have to effectively put these three methods of measurement themselves together?
Not at all. We don't expect from the contractors to have any level of sophistication that they would make any such methods on their own. It's not their job anyway. They're there to build projects. That's our job. Our job is to build the back-end software that can leverage those three sensors together and give you a common method of scanning your asset in a very convenient way. The final implementation is supposed to be that you can pick up this device, walk around with it, scan any site you want, have with you a tablet or some other device. You need the screen to see the outcome as you're scanning. And then through that screen, use that to make better scanning decisions as you walk along. And as soon as you're happy with the outcome, because you can see it on the screen, you stop the process and you have an outcome that doesn't need any post-processing. And it already has the points, the pixels, and the near infrareds all registered to each other, again, without the need for post-processing. And like you said, this is not commercial yet. This is still in research phase. Mm-hmm. But considering we have 5 industry partners, there is a very large impetus to move that into the commercial space once it's done.
Again, going back to the digital twins that you mentioned earlier, obviously, based on what you've said, computer vision plays an important part in the capture of the asset data. So from what you discussed, what is the key missing part here? Is it this type of hybrid method that you're now piloting and testing, or are there also other, maybe not so technology related aspects that we should bear in mind? You mentioned cost being one of those.
Very good point. So the general principle is that when you're building something new that people haven't been using so far, it is very hard for people to see the value, the benefit. So if you've never had a digital twin, you don't actually know how valuable it is. At the same time, we have to have one so that we can derive its value. And we have a chicken and egg problem here, which is very common also with my colleagues in structural engineering, who would like to see these kinds of data sets on top of which they can go and do their own structural analysis and give us the as-is actual performance of an asset. But without the data, they cannot do that. And so with regards to how the industry perceives this, I would say that that's exactly why we need very low-cost methods. Because if the method is very, very cheap, people would be willing to try, and you'd see more and more examples of that. If the method is expensive and you need to spend, thousands or hundreds of thousands or millions in some cases to just build one model, then very, very few use cases will actually do that.
So regards the research that you're doing right now and the future research, does that largely entail in trying to come up with ways of making this more cost effective?
Yes, that's absolutely the case. We are trying to move away from expensive laser scanners and into very small, cheap devices that can deliver the same or better outcomes pretty much through software. Same thing with our detection methods. We're trying to get to software that can simply receive from the user the input data, and then effectively, with very little to no human involvement, produce the model. Now, that's not going to be 100% automatic. It's important to mention that there are always specialty objects and other kinds of objects that the system is not going to know how to recognize. But there goes the 80-20 rule, which says that 80% of the objects in an asset belong to 20% of the most frequent object type categories. Therefore, if I can capture that 20% object types, I can do 80% of the job and then have someone come in and just work on that last 20% rather than having to do everything manually.
Which I take it most of it to date has been largely manual.
Right now it's all manual, and it's an incredibly boring process. Can you imagine modeling from column to column, wall to wall in very large facilities? That is a lot of time.
Absolutely, yeah. So apart from what you've discussed here with computer vision, you also have vast experience and an array in research, particularly when it comes to construction management, civil engineering. I'd like to ask you, in terms of everything that you've witnessed to date and experienced in your own research career, what type of advice would you give to early career researchers trying to make an impact within this particular field, so construction and the built environment?
Maybe my advice is a bit unconventional, but I would say try to be very, very critical of what you see going on around you to try to really understand where the real problems lie. It is very common for researchers to do something that perhaps is convenient or conventional. That will not take them very far. The reality is that if a problem was in fact equally visible to everyone, someone else would have done it. It does take effort to understand the problem in detail. It does take effort to pick the right problem to solve, the one that actually has impact, and to understand that perhaps that might be a big problem. And you know what? So what? You have an entire career in front of you to solve it. Perhaps you should focus on dissecting it into smaller chunks and trying to have baby steps in there, small successes, until one day you can get to a big success. That would be my main formula.
And regards the work that you've talked about to date, where can our listeners find out more about your research work and some of the resources associated with it?
Well, first of all, as a general overview, there are at least one or two presentations that I've given that have been posted on YouTube. And it should be easy for people to look me up there and just watch it to get a general overview. Beyond that, several students of mine have done their own YouTube videos highlighting their work with several examples. And lately, fortunately, several of our conferences are picking up on the concept of videotaping the presentations at conferences and posting them on YouTube. So there are several conference YouTube channels where you can watch several of our papers there. Other than that, there's always the papers, journal and conference papers. And of course, if someone wants to try, we are publishing data sets gradually. So we have several data sets available, some of them already online, others available upon request. Perhaps the most important asset that people can try is our own research platform called Gygex. Gygex is effectively what we call our MATLAB on steroids. It's a very nice little system that simply combines together all the basic tools you need to play with these kinds of data. You have OpenCV there for all the computer vision tools. You have PCL for all the point cloud tools. You have maths libraries for maths. You have TensorFlow integration for deep learning. So there's several things you can combine in one space. I forgot to mention the IFC engine for BIM files. And a lot of the examples of research I mentioned today has happened on top of that platform. It's open access and available for free on GitHub.
Nice. And is this something that you've put together with your colleagues?
It's been a painful process to get it to where it is today, but the lead authors are my students. And one after another, they kept on improving it. We're now effectively at version 3 of the platform. And there is many examples also available for people who want to test specific ones.
Thank you for tuning in to listen to Beyond BIM podcast. If you enjoyed this episode and want to hear more from our latest episodes, then you can visit Beyond BIM, which is available on SoundCloud and iTunes and all the other major podcast providers.